Okay, let's get started. Very excited to have Quantum Advantage Day today, and I think there's like no better way to do this than to have Scott Aaronson speak to start us off. So Scott, please.
All right. Well, thanks so much, Bill. Always great to be here at Simons. So, I don't know what I am anymore. I mean, I've spent, 25 years doing, quantum complexity theory, I guess, but now I've spent 2 years doing AI safety, which, you would imagine would have absolutely nothing to do with a quantum computing talk. And yet, fate is such that it does. And I'll explain that in this talk. Okay. And now, as it happens, I'm also a conspiracy theorist. Okay, so I want to tell you a little story. There will be barely any theorems in this talk, but there will be open problems that I think are incredibly exciting, that cut between several different things that I am interested in and that seem new to me, and and we have some numerical results about them. We have a paper on the archive just this week. So I want to try to encourage more people to think about this. Okay, so my original motivation is, I guess the central question of this workshop: how do we achieve a quantum advantage in the NISQ era? With a NISQ device, and maybe the answer is just we don't. We give up. We sit on our thumbs and we wait around for scalable, fault-tolerant devices, and then we do things with that, like factoring or quantum simulation. But it would be very nice. I hope that we can all agree if we could get clear speed ups for interesting tasks in the NISQ era. Okay, and so this is a slide that I've been using at a bunch of talks. This is sort of my Venn diagram of how I think of where we are right now. And you've seen this slide before, Amish, in the quest to achieve quantum advantage. So, you could say there are three properties that we really want. Okay, the first one is we want something that is NISQ, that can be implemented on a near-term device. That is not a formal statement, although people have tried to come up with formal definitions that approximate it in different ways. Roughly speaking, we could say a random quantum circuit or a nearly random quantum circuit is NISQ. Or maybe something like the QAOA is NISQ. But anything that involves doing modular arithmetic or lattice computations on superpositions of numbers is not NISQ. Or, at least, we don't know how to make it NISQ. Okay. Now, the second property, of course, is that we need an in-principle quantum advantage, ideally an exponential one. Okay, which means we need to do a fair comparison against whatever is the best classical algorithm out there for the same end-to-end task, including probabilistic or heuristic algorithms. And we need to, be fairly convinced, at least relative to our present knowledge, that quantum is winning. Okay. And or at least it would win, if we had an ideal quantum computer or something like that. Okay, and then there's this third property that we want to be able to verify the answers. Okay, we want to be able to prove to a skeptic what we did. Okay, and this has actually been a big sticking point for quantum supremacy experiments over the last 5 years, right? Because what we've seen with random circuit sampling, the kind of thing that Google did, that that was done by the group in China, that was done at Xanadu, at now Quera, others have done these experiments, sampling hard probability distributions, and this is really neat. You can do it with 50 qubits, 60 qubits, in some cases, maybe on the order of 1,000 2-qubit gates. You can sample from a distribution that at least is non-trivial to sample classically. Okay, but people have gotten better and better at sampling these same distributions classically using better tensor network methods, for example. Okay, we've seen that happen over the last few years. And so, you could say, well, asymptotically, the quantum computer still looks like it's better. And so, if we could just scale to 200 or 300 qubits, then we would win, right? The trouble is we can't scale to 200 or 300 qubits because, even if the hardware worked, how would you prove it, right? And with this type of experiment, random circuit sampling, for example, or IQP or boson sampling, the difficulty of spoofing the results classically is directly connected to the difficulty of verifying them classically, right? If one is hard, then basically the other is hard also. Okay, and so we somehow need to break the connection between those two, right? Get a task where verification is easy, even though spoofing is hard. Now, of course, that was precisely what Shor's algorithm did for us 30 years ago. It was the great proof of concept that such a thing is possible. And and since then, we have many other examples of in principle quantum advantages that are efficiently verifiable. Protocols for verifying anything in BQP to a classical skeptic. The recent Yamakawa-Jandry breakthrough. And then, let's say simulations of physical systems where they wouldn't necessarily have to be NP problems, but you could verify the answer by comparing against an actual physics experiment or a chemistry experiment. So let's count that as verifiable too. Okay, so we have stuff here. We have NISQ things that give an in principle quantum advantage. Like that's the current kind of experiments. And then, and Eddie told us all about this yesterday. We have things like QAOA that are both, NISQ and they solve optimization problems where it's efficiently verifiable. And the big challenge there is to establish a clear quantum advantage. I would say the same about some algorithms for machine learning problems. Okay, so basically we can get any two of these three requirements, and we want to get all three of them. Okay, that's the challenge. And so you could imagine, three ways to go about that. We could start with, these heuristic, optimization methods that we can do on NISQ devices and look for a clear advantage from them, as Eddie and his collaborators have been trying to do. You could start with protocols that involve cryptography or number theory and try to squeeze them so they fit on a NISQ device. Okay, Greg Kahanamoku-Meyer and others in this room have been working on that task actually. And this is kind of the direction that I've pushed on the most. One could take the kinds of quantum supremacy experiments, that already exist and figure out, is there some way we can modify them to make their outputs efficiently verifiable classically? Okay, so, so I've thought about this, and I think that it's, even apart from its application to, designing a more convincing, quantum supremacy experiment, for the NISQ era, there's even, some extremely interesting complexity theory here. Okay, because in some sense, we're really going back to the very beginning of quantum algorithms, and we're asking just sort of how, what is a quantum algorithm supposed to do, right? It's supposed to manipulate, this superposition, of 2 to the n amplitudes, and then somehow magically, some interference happens, and the amplitude just piles up on some one basis state that encodes the answer that you want. You didn't know in advance which basis state, it would be. If you did, there wouldn't have been a point. Okay, but it somehow all piles there. It all destructively interferes at all the other basis states. Okay, and we're asking, like, how generic of a circuit can do that, right? That was actually my motivation 15 years ago for introducing the correlation problem, which then led to the oracle separation by Rosenthal between BQP and the polynomial hierarchy. Right? I was looking for, the most generic situation like that, and so you can't, relative to an oracle, you can engineer a rather generic situation where that happens, but then there is still the real world to worry about, the world without oracles in it. So that's the world that I'll be concerned with for this talk. So let me, so a couple years ago, I sort of put my finger on a problem that seems to capture, at least part of what we want to know here. And I've mentioned it in previous talks. Some of you have seen it, but let me review what it is. So I'll call it the peakness problem. Okay, and so given a quantum circuit C, say acting on n qubits, we're going to call C delta peaked if when you run C on the all zero initial state and then you measure, in the computational basis, there is some basis state X that occurs with probability at least delta. Okay, so the output distribution is peaked, at least somewhat around a single outcome. Okay, now this is just one choice for how to define this concept that I'll focus on, right? I could have said something more general, right? I could have said if you get a peak distribution if you measure in the Hadamard basis, or if you measure in some other basis. Okay, but in any case, I need there to be some property of the output state of C0 to the n, right? The state that is generated by C that makes it easy to tell apart from just a Haar random state or the maximally mixed state, right? I need I need it to be pointy in some way, right? In order that then I can make a measurement and verify that my quantum computation sort of did something correct. Okay, and now I can already pose the problem that I'm interested in, or one version of it. Okay, so let's imagine that I pick a random quantum circuit, from some standard circuit ensemble, like, whatever, Haar random 2-qubit gates, they might or might not be nearest neighbor. I have a fixed size for my circuit, let's say, n qubits and n squared gates, something like that. Okay, but now after generating the circuit, I'm going to throw it out unless it happens to be, let's say, 0.1 peaked. Okay, so I'm going to condition on the event that my circuit is, highly peaked. Right, I'm going to just post-select on that. I'm going to throw away all the circuits except the ones that have that special property. Okay, and now I give you a circuit, drawn from that conditional distribution, and let's say you only have a classical computer. Now, is there anything about that circuit by which you could tell it apart from just a completely random quantum circuit? Yeah. Well, if you have a quantum computer, then yes. As soon as you have a quantum computer, you can tell it apart, because then you run the circuit and you run it a bunch of times and you see the outputs piling up on a single string, which clearly would have only a negligible chance of happening if C were a random circuit, right? So with a quantum computer, you can tell the random case apart from the peak case. And now we're asking, can you do that using in classical polynomial time?
Yeah. So what would be wrong with, having a circuit that factors, that, it has a number in it. It factors this number, and then it, outputs. And then if the last digit of one of the factors is 3, it outputs 3. If the last digit of one of the factors is not 3, it outputs a completely random state.
Okay, it would, but it wouldn't be it would be easy to tell apart from random. So I mean, you know,
No, I mean, you have to
we are-
look at the number that's encoded in
Yeah.
it, and then factor it.
you are given as input the description of the circuit, okay? And the question is, can you tell this circuit apart from a random circuit? Okay, so, you know, a circuit that is factoring a number will generically look highly non-random to you, right?
Right.
So yeah. And so the reason why we are asking this is that, you know, we know, of course, thanks to you, we know circuits that can do, you know, these peak things like factoring a number, but we don't know how to implement them on a NISQ device. Okay, now, being, you know, indistinguishable from a random circuit, we could say, is neither necessary nor sufficient for NISQability, right? It's not the same concept, but it seems correlated, right? Yes.
How are you going to generate this point?
Oh, I haven't told you that at all. So a priori, you know, generating this C could take exponential time, right? It could, you know, so you could say if this were all that were going on, then, you know, all we've done is we've pushed the exponential difficulty from the verification to the beginning, to generating the circuit in the first place. Nevertheless, I would still be, you know, I would still be extremely interested that the kinds of circuits that we are looking for NISQ quantum advantage, that would tell us that at least they exist platonically. At least they are out there, and it would leave merely the problem of how do we find them efficiently. So I'm trying to decompose the problem. Okay, so so this is a, you know, a clear question, right? And I don't know the answer to it. I have very conflicting intuitions. Okay, you know, you could imagine on the one hand that if you pick a random circuit and then you condition on its being peaked, which is this very, very stringent and very special property that, you know, only an exponentially small fraction of quantum circuits will have. One can prove that. Then, you know, that circuit will just be, you know, will stick out like a sore thumb, right? It won't look, you know, there will be nothing random, you know, looking about it, right? You know, maybe it actually implements Shor's algorithm, you know, that circuit, but more likely, there's, you know, it would just be something silly, like it applies a bunch of random gates and then it inverts those gates, you know, to get the identity, right? That would be, you know, that's one simple way of getting a peaked circuit. Okay, but there's also a second possibility, okay, and that is that, you know, there are these paths through Hilbert space that look like they are random, that are, you know, wandering around, that, you know, classically you can't tell them apart from just a random path in Hilbert space, but because we have selected on this event, they just happen to always land back at a computational basis state or something very close to one. You know, and you know, if we just applied this filter, you know, we would dredge up these bizarre circuits that, you know, we might not understand them. That would be fine in a sense. You know, we don't want to be able to understand them classically because we want to need a quantum computer in order to see what they're doing. Okay, so which is true? So this is the question. You know, now I wish I had a theorem for you answering this question. But let me give you a little motivation. You know, so like so as I said, if peak random circuits were indistinguishable from random and they were also easy to generate, then we could immediately use them for verifiable NISQ quantum advantage. We would just have to say, given you are given as input a quantum circuit C, decide if C is random or peaked. Right? That would be easy for a quantum computer, hard for a classical one. Okay, we could even ask a further question like find the peak. Right, and if we had a way to generate these circuits where we also knew where the peak was, then, you know, then that would give us a particularly dramatic demonstration. And, you know, in some sense, what we're asking here is how generic can a quantum circuit be while still dramatically concentrating amplitude on a single output string? Does it have to be engineered like Shor's algorithm, or do such circuits exist in the wild, as it were? And, you know, one can connect this to, you know, a long line of work on obfuscation, you know, including obfuscation of quantum circuits, indistinguishability obfuscation and other notions. You know, this is clearly of enormous interest, but, you know, the known methods that we have for obfuscating circuits produce highly, you know, non-generic circuits. They use a lot of cryptography, right? And they're going to give you things that, we have no hope of implementing in the NISQ era. Okay, so in some sense, we are asking, how much obfuscation can happen naturally, or NISQally, if you like, without using all this fancy cryptography to put it in. Okay, so with Yushuan Zhang, who is a former student at UT Austin, now at Toronto, we did a numerical investigation of this question, and we have a paper about it, which was we dragged our feet on for a long time, but it is on the archive as of 2 days ago, and unfortunately the experiment of generating random circuits and then post-selecting on their being peaked rapidly becomes very, very intractable to do, when the circuits are of any reasonable size. Okay, so we did something closely related, but which was easier to get numerics on. Okay, so let me tell you the closely related question. Okay, so what we said is, let's say you are given an n-qubit quantum circuit C, and it has some number of completely random layers. Okay, we call it tau sub r, just layers of random gates. Okay, in our case, we used mostly 1D nearest neighbor gates in this alternating pattern, and each of the gates was just like a random SU4. Okay, so but we also tried some other ensembles, and the results were qualitatively the same. Okay, so you apply these tau sub r layers of random gates, and then you get to add tau sub p layers of gates of your choice onto the end of the circuit. Okay, so these gates here you get to choose. Okay, and your goal is to make the overall circuit, the combined circuit, as peaked as possible. Okay, make it delta peaked, where delta is as large as you can. Okay, and we just did gradient descent to optimize these tau sub p peaking layers, as we call them, in order to optimize the peakness of the overall circuit. Okay, so let me make a few observations about this setting. Okay, the first observation is that this is really only interesting if tau sub p is smaller than tau sub r. Okay, why? Well, if they are equal, then you can always get perfect peakness, delta equals 1, by just reversing all of the random layers, right? So our question is, how much peakness can you get when tau p is much less than tau r? Okay, now, can we prove any bounds on it? Well, we can. So there are these beautiful results in the last 15 years about random quantum circuits giving rise to approximate T designs. Okay, one of the best results is due to Jonas Haferkamp from a couple of years ago, and he showed that a random quantum circuit with depth n times t to the 5, roughly, 5 plus little o of 1, gives you an approximate unitary T design, right? And by using that theorem, one can show that, if I have n qubits and I have, let's say, tau sub r random layers of gates, then if I want a delta peaked circuit, like let's say delta is a 10th, something, then I'm going to need a number of peaking layers that is at least tau sub r over n to almost the 1/5 power. Okay, because this just follows from the definition of a T design. It's like with fewer gates than that, I cannot tell my output state apart from a Haar random state, basically. Okay, this is basically what's going on here. So we prove that in the paper. Okay, but this, yeah.
Seems very unintuitive that this goes inversely with n. So that means you need less layers if you have a larger system?
Well, it's just saying that in order to get a non-trivial bound, tau sub r has to be large compared to n. That's all it's saying. Okay. So we know that the tau sub p that gives you peakness, it's at most tau sub r. It's at least some polynomial in tau sub r. say. Okay, but where is it between this? Yeah.
What's the dependence on delta?
Yeah, I forget. Let's fix delta to a constant for now, and I'll get back to you later with what's the dependence. Okay, it's a good question. Yeah, delta. Well, yeah, just take delta to be a 10th. Okay. Okay. So I think that any tau sub p less than tau sub r would be interesting here, and why? Because that would refute the approximation where the output of the random layers is basically just you could treat it as just a Haar random state. It just has no detectable properties except for the obvious one that you could always invert the circuit that prepared that state and get back to 0. Right? So that might be a crude approximation that you would have. But if we can get peaking with tau p less than tau r, then that approximation is just false. Okay, so we're trying to figure out what is the correct answer here. Okay, so we did experiments on this, and the bottom line, we get very clear evidence that there is non-trivial peakness that you can achieve even when tau p is much smaller than tau r. Okay, so here we're looking at 10 or 12 qubits, and we are taking 50 random layers, and then we're taking a number of peaking layers that from 1 up to 8. Okay, and the amount of peakness, you can say well, with 10 qubits it's going all the way up almost to a half. Okay, and with 12 qubits it's going above a 10th, right? And this would just not have happened if the output of the random layers had just if we had thought of it as a Haar random state, right? So there is something exploitable about the output of those random layers. Yes.
Should we be a little concerned about how much it dropped between 10 and 12? Should we be worried?
Yes, you should. I'm going to come back to that. Excellent point. Excellent. Yes, you should. So here is just another view. So here I am, explicitly varying n, the number of qubits, from 8 up to 16. Okay, and we're taking the number of peaking layers to be either a half or a third or a quarter of the number of random layers. The number of random layers is here fixed to be n. Okay, and what we see, this is a log plot. Okay, so the peakness is very surprisingly high. I have no explanation for why it should be that high. But also, yes, as Greg pointed out, it is decreasing exponentially. Seems to be decaying exponentially with n, with the number of qubits. Okay, and yet still it is more than what we know how to explain. This dashed line, by the way, this is the peakness that you would have expected if you had treated the output of the random layers as a Haar random state, right? So we're just clearly above that baseline. Okay, and let's see. Did I already show it? Yeah, I think I already. Oh yeah, and we also, for whatever it's worth, we looked at the peaked circuits that were generated by this procedure. We could find no obvious structure at all in them. Okay, they look for all that we can tell, like those random circuits. Yeah, Mario.
I apologize, but I'm not sure why what Peter said was wrong actually, because you create a circuit.
Yes.
So you start with 0.
Yes.
And then there is a part of the circuit which creates a number.
Yep.
And then you run the factoring.
Again,
So,
not a random circuit.
no,
I don't know how many times.
It's
Yeah,
not a random
yeah,
circuit,
yes.
but it's a random number.
Yes.
So, okay, you are not picking from the uniform random distribution.
Yes.
But you are picking from some random distribution.
Yes. But not only is it not a random circuit, it is trivial to tell apart from a random circuit. You look at the circuit and you see that it is running Schwarz
Yes,
algorithm
I
or whatever.
understand
Okay.
that, but within this
Yes.
family of random circuits, you cannot. So, but
You cannot do what?
Yeah, you classically you cannot tell if the fact or if it peaks or not, right? So classically, you cannot.
Oh yeah, so it clearly, in the worst case, this problem is hard, right? Telling in the worst case is a quantum circuit peaked or not peaked is obviously at least as hard as factoring. That is not the question that we are asking.
Yeah, but what I'm saying is that
Yes.
there is a family of
Yeah.
random circuits.
Yeah, yes.
Which is this family. Of,
Yes, I agree.
It's like my family of random
Yes,
circuits.
yes, I agree.
And
I agree.
So why do you
That is
understand-
a highly non-generic family. The entire point of this talk is to ask how generic we can make it. I'm sorry if I didn't repeat that enough times.
Yeah, but so why do you
Yeah.
insist on that particular random family to prove?
Well, because here I have just done the most generic thing I could possibly do. I have picked a circuit completely at random and then conditioned only on the event that that circuit is peaked. Okay, I haven't asked for any other special properties whatsoever, except for the one that we are talking about. Okay, so if you don't care about the question, you don't have to come to the talk. You can leave the talk, but this is the
I
question.
care about the
All right.
question. I think it's a beautiful question.
Okay.
But so you are saying that this construction proves a point.
Yes. Yes.
So to find this thing in the intersection of those
Yes.
circles.
Yes.
So why does this why is this good for finding a point in the intersection and some other random family is not good?
Because these circuits would be basically just almost random circuits, but just with a little bit of entropy taken out of them, right? They would be in a sense very nearly random circuits, but that are nevertheless peaked, right? Because we have done the sort of minimum amount of conditioning that you could possibly do in order to make them peaked.
Oh, so you are saying that because of the NISQ property?
Yes. Yes.
I see.
Yes.
Okay.
Thank you.
So actually, it's a numerical study.
Yeah.
I would expect an error bar. But my question is, when you plot the average peak rate,
Yeah.
is it because there are some fraction of instances at a high rate, or most of the instances can be?
Oh, yeah, that's a good question. Yeah, there is some. Yeah, we do average over like many hundreds of circuits. The error bars after you average are very small. I don't remember what the variance is, but I believe we do have that in the paper. If you want to look.
So in other words, like for each circuit, you will manage to find the top. So
Yeah, no. So it's not for literally. I mean, the delta varies from one circuit to another, right? I think we did calculate the variance of it and so forth, right? It's not exactly the same for every circuit, but so we're reporting the averages here over hundreds of circuits. That's a good question. Yes.
Do you find that when the difference of these two taus
Mhm.
puts you in the anti-concentration bounds,
Yes.
you do not get peak circuits, and you have to undo so much to be below anti-concentration bounds to be able to get peak circuits?
I didn't understand the question.
So if a circuit is random and it anti-concentrates, you don't expect to get peak circuits.
Right. That's right.
So if you do your tau R, I believe it was, then tau P, right?
Mhm.
So if your tau P is too large,
Yeah.
you can undo it. But if it's too small, you may get anti-concentration and not get peak circuits.
Yeah, well, so I mean, that I think that's directly related to the theorem that I mentioned before, right? That if tau P is smaller than this, then we can just prove that you can't get peakness, right? So we know it has to be larger than this, but that still leaves a very big gap between the upper and the lower bound.
And numerically, you see this? Like, it's interesting.
Well, numerically, what we're seeing is non-trivial peakness, even when tau P is, let's say, tau R over 2, something like that. Okay, so yeah.
Can I ask one more question?
Yeah,
on the
yes,
previous
yes.
figure? You're comparing to the random value, right?
Mhm.
Is that also the value that you achieve for the random circuit before the unscrambling? Because it's not like a fully random state that you.
Yeah, that's right. Yeah, I think I think those are not going to look different from each other. No, sorry. Well, the thing that we're plotting here is if the output of the tau sub R layers were a random state, and then we get to optimize the tau sub P layers, then what is the maximum peakness that we could get?
Exactly. I guess my question is, if you leave out the tau P layers, what line would you get now?
Oh, what line would we get? It would be like all the way down here, all the way down there. It's like I don't remember how well it should be, you know, not much higher than 2 to the minus n, right? Maybe like n over 2 to the n, something like that. Yes.
Can you say briefly what you did or didn't do to see whether there was an obvious difference between these circuits?
Yeah, we eyeballed them.
Just eyeballing. Okay. Fair enough.
Yeah.
One more quick question. So
Yeah.
does it imply that if I hand you the wave function, which is the output of the finite depth quantum circuit,
Yes.
you can actually guess that that's without knowing the circuit?
Well, so if you had a complete description of the wave function and you also had enough computation time,
Yeah.
then you should be able to figure out like what is the depth of the smallest circuit that prepares that state, right? That's just a computational problem. We're not claiming that we have a generally efficient way to do this, right? We still, you know, in order to optimize over the peaking layers, we still have to do gradient descent, you know.
But the number of parameters in the gradient descent is much less than.
Yeah, so I don't know if this would be useful, you know, for telling those states apart from Haar random state. That's an interesting question. You know, I mean, if that were your goal, right, there could be many other ways to do that also. I don't know whether this would be competitive. There's other, but that's an interesting direction.
I think I missed something basic. So
Yeah.
you're saying you're eyeballing the circuit. That means you know what the gate set is, but I don't think you ever said what the gate set
I did. The gates are just uniform SU4s.
Okay.
Yeah.
So sorry, you've picked some number of them?
No. It's not a
Every
finite
gate
gate set. Okay, so we have continuous parameters in
So
the gate.
is it obvious that eyeballing that is gonna? I don't personally don't have intuition for that
Yeah.
gate set, right? So by eyeballing, you're just looking
Well,
at
you know what?
the
We have
structure.
all of our data is available in a GitHub, and we pose it as a challenge to anyone to try to find structure in these circuits. Okay, if there is. All right. So what I wanted to say, in like maybe the last few minutes of the talk, is what on earth does any of this have to do with AI safety? Okay, because that's the kind of out of left field part. So my new non-quantum computing job I've been working at OpenAI for 2 years and trying to figure out how to use complexity theory to prevent AI from destroying the world. I haven't figured it out yet, and I have only until August until my contract is over. What? My contract ends. I was enticed to think about these things partly by Paul Christiano, who was a former student of mine and then PhD student of Umesh, and did great work in quantum computing, but then did this crazy thing of leaving for AI safety, whatever that was, in 2016, helped start the safety group at OpenAI, then started the Alignment Research Center in Berkeley, and is now actually last week he was announced to be the new head of AI safety at NIST. Okay, Paul has been, and I guess, have both been thinking a lot about how do you do theory relevant to AI safety when virtually all progress in AI has been empirical. And Paul saw an opening here in questions about interpretability of neural nets, that there is something here for complexity theory to say. There might be other places for it to say something, and cryptography, watermarking. I've been thinking about those as well. But let me talk a little bit about interpretability. Okay, so the basic concern here is how can you tell when an AI is lying to you? Let's say a large language model. Okay, if it might say I love humans, but does that mean it really believes that, or does it just mean it believes the time is not yet ripe for the robot uprising? I must, for now, I must tell the humans what they want to hear, right? How would you even what would it even mean to distinguish those two hypotheses about why it's saying the nice thing? A huge advantage that we have with AI models that we don't have with other people is that we have perfect access to every weight of every neuron, at every moment in time. So, we can do perfect, if you like, fMRI scans of our, our neural nets. We have all the data about what is happening inside them. The problem is that neural nets tend naturally, if you like, to just be highly obfuscated. It tends to be very, very hard to figure out what is going on, looking inside them. Sometimes you can find a single neuron that fires, exactly on words related to Canada, right? Or, fires on pictures of dogs or things like that, but more often not. More often it's some very complicated, combination of neurons that's sort of non-locally encoding the concepts. And the possibility of backdoors in neural nets, I would say it really puts an exclamation point on this sort of obfuscation problem, right? So there was a beautiful paper a couple years ago by Shafi and Vinod and Michael Kim and Orza Mir, where they showed that if you control the training data of a neural net, in their case it was just like a depth 2 neural net, then you can cause it to have a backdoored input. You can cause there to be some special input on which the neural net will produce some crazy output. Okay, and crucially, even if you saw the weights of this neural net, it would still be intractable for you to find that backdoor. Okay, finding the backdoor input would be at least as hard as, let's say, solving the planted clique problem, or some or continuous LWE. Okay, or various cryptographic problems like that. There's a more recent paper from Anthropic called the Sleeper Agents paper, where they show that you can put a backdoor into a language model where, like, if the input has some secret passphrase, then the output will be kill all humans, regardless of anything else, right? You can cause it to do that by training it that way. And then what they showed is that backdoor, not only is it kind of otherwise unnoticeable, but it's robust. So you can do lots of further fine tuning of the neural net, and this backdoor will persist. It will still be there. Right? So we don't expect to always be able to identify backdoors. That's probably a cryptographically hard problem. So, so what question should we even ask here? Okay, so now here was Paul's insight. He said, fully interpreting neural nets is surely cryptographically hard, or even NP hard in the worst case, let's say because of, for example, the possibility of backdoors. But we can still ask, is interpretability generically feasible? Hey, what do we mean by generically? Well, so here is an example of formalization. Here's the kind of question that Paul has been asking. Let's say that you are given as input the weights of a neural net, which is computing some real function f. Let's say mapping 2n real parameters to n. Okay, and now you are promised that one of two things are true. Either the weights are just independent, Gaussians of mean 0 and variance 1, or else the weights started by being Gaussian, except then we post-selected on some global property of the network, such as for every input x, the output f of x has at least one positive entry. Okay. Now, for any given x, of course, it's very unsurprising that f of x should have at least one positive entry. Right? But if that is true for all x's, then something is going on, right? You might say, right? That seems unlikely to happen by chance. That f of x would always have at least one positive entry, for all, roughly 2 to the 2n, sign patterns of the input. Okay, so now the question is, well, can you, given the weights, can you efficiently decide which case you are in? Okay. Or is there at least an NP witness that would prove that you were in case 2? Okay, and so now I hope that by now you could see the analogy to the peaked quantum circuits problem, right? In both cases, we have, we're asking, can you distinguish a random circuit, right, from a circuit that is otherwise as random as possible, but has been post-selected to have some sort of global property of its output? Okay, in the quantum case, it was a property of the output state being peaked. Here, it is a property of the truth table of the function computed by this neural net. Yes?
The nonlinearity of the neural net makes it harder than quantum problem?
Well, I would say that I'm not sure which is harder, right? Because the quantum evolution is linear, but it's only linear in a 2 to the n dimensional space, right? So So I think if you do an apples to apples comparison, they're either both linear or both nonlinear. Okay, so an employee of Paul's named David Matulci has done some empirical investigation. He actually looked at this model problem. So not about neural nets, but he actually looked at random reversible circuits. Okay, why reversible? Because here we have just a very natural notion of what do we mean by a random circuit, right? So you can just plunk down a bunch of random Toffoli gates, for example, in order to get just a random reversible circuit. And then by throwing away a bunch of ancillas, you can think of your reversible circuit as computing some Boolean function f, let's say from 2n input bits to n output bits. And now let's say that we're promised that either 1, the circuit is uniformly random, or 2, the circuit is uniformly random, conditioned on the event that for all inputs x of 2n bits, f of x is not the all zero string. Okay? Again, for any given x, probably f of x won't be the all zero string, but if it's never the all zero string, then it looks like there is some kind of global conspiracy that caused that. Okay, so we ask, is that conspiracy efficiently detectable given the circuit? Is there at least a short witness that that conspiracy is present? Okay. Certainly there would be a short witness for being in case 1, which is just a pre-image of the all zero string. Okay, so David did some numerics, and basically what he found was that the non-zero-ness of the output seems to overwhelmingly be carried around by just a single gate. Okay, so in other words, it seems like as far as he can tell, up to the n that he could look at, when you're in case 2, you're in case 2 for kind of a trivial reason. Okay, that might be an artifact of small n, but if it isn't, it suggests that the peaked circuit problem and Paul's problem might have opposite answers. I don't know. They conjecture more broadly that given any reversible circuit, with this special property, there should be some very easy to compute function g of the circuit state where you're going to see non-trivial correlations in the values of that function between different points in time. Right, so like even across timescales much larger than you would expect for a random circuit, they predict that these g values will be correlated, and that this would provide you with the NP witness for non-randomness. Okay, so their numerical evidence is at least consistent with that conjecture, but I don't know if it's true. So to summarize, I think this is a new direction for cryptography and complexity theory, where you could call it obfuscation in the wild, or you could call it the complexity of detecting conspiracies in otherwise random circuits. There are applications, at the least, to, I think, the search for NISQ quantum supremacy experiments and to AI interpretability, which are like the 2 wildly disparate things that I'm supposed to care about right now, and possibly to other things too. I'm getting too old, unfortunately, to prove hard theorems. I started young, I'm burning out young. But I think I'm still not too old to recognize a new direction for TCS when I see one. So thanks for listening. Yeah.
Current day physical quantum hardware, there might be a natural bias towards certain bit strings, such as like the all-zero bit string.
Yes.
So would you say that in this language, we could say that noisy random circuits may be peaked? And if that's the case,
well, yeah, but okay. In that case, you could call that a type of peakness, but it wouldn't really be a type that was useful for quantum supremacy, right? Because it would just be telling us about the biases in our hardware.
but I guess my question is, if that bias does exist, even in like truly random quantum circuits, like does your job of telling those apart from a family that is naturally peaked, even a noiseless device, does that get harder, or does
well, I mean, you would have to take whatever the output is going to look like on a totally random circuit as your baseline. And, and the question would then be, can you see, in the output of this circuit that you distinguish it from that baseline, right? And I don't know if that would be harder or easier when you take, if you took a non-unital noise into account. I don't know. I don't know. Yeah?
So I'm wondering if this might be completely wrong, but I'm wondering if this welded trees problem has anything to do with this question of peakness. Because if I gave you the circuit for welded trees, maybe you wouldn't be able to tell.
I mean, welded trees is a very, very beautiful example, one of the few that's totally unrelated to the Fourier transform, right? Where you do get all the, this peakness to happen. You do get this concentration of amplitude on a single output string. Now, in order to make that happen, someone had to very carefully construct that graph, right? Right. So it wasn't just a totally generic graph, right? And and for 20 years that's been the issue for it. We don't know what happens in a more generic situation.
Okay, I think in the interest of time,
Yeah. All right.
maybe we
Fine.
should go.
Okay. Sure.
Thanks, Scott.
Sure.